This is the third video of AP Biology Unit 3 on cellular energetics, and this video is going to cover a concept called redox, which is not technically part of the AP Bio curriculum because it's a chemistry concept, but it's important in understanding photosynthesis and cellular respiration, so let's dive in. So, a little bit of review to start. What is that table in the upper right showing? What are those colors showing? Don't worry too much about the numbers. What are those colors showing? And then on the left, how does that relate to that cartoon? So this table is showing electronegativity values. And so the higher the electronegativity value, the more affinity an atom has for an extra electron. And you can see that the ones in the upper right of the periodic table have really high electronegativity values, like oxygen, for example, has a high electronegativity values. The ones on the very right are noble gases, so those are stable and they don't want more electrons at all. The ones on the left generally have lower electronegativity values. All right, so how does this relate to this cartoon? Well, electronegativity, if you remember from Unit 1, determines bonding. And so if you have two atoms with different electronegativity values, if they have slightly different electronegativity values, they'll form a covalent bond where they'll share those electrons. But if they're not sharing it equally, one of the atoms is sort of hogging those electrons, and that's due to its higher electronegativity value, so that would be a polar bond. Let's talk about a complex concept by a silly little picture. So what we have here is a molecule on the left with control of an electron, and then over on the right, imagine that ox represents a molecule with a strong tendency to gain electrons. What do you think is going to happen in this situation? So what's going to happen is this ox, which has a strong tendency to gain electrons, is going to do exactly that. It's going to gain control of the electron from the other molecule. This is known as an oxidizing agent. Oxidizing agents steal or hog electrons, and a common oxidizing agent is oxygen, which is why we've represented it with the ox. So some terms you need to be familiar with here is oxidation and reduction. So the molecule on the left has been oxidized, and the molecule on the right has been reduced. Why do these terms make sense? So oxidation makes sense because it's often oxygen that causes this. Now it's not always, which is a bit confusing, but if you just remember that oxygen is a common oxidizing agent, the molecule that has been kind of attacked by oxygen is what's been oxidized. Now the molecule that has been reduced, that makes sense because it's gaining an electron. Remember that electrons have a negative charge, so if it's gaining control of electrons, its overall charge or partial charge becomes lower. So the term redox comes from a combination of the term reduction and the term oxidation. And a redox reaction is where a reduction and oxidation reaction happen at the same time. So you have one molecule that is reduced and the other that is oxidized. If you take a look at the picture on the bottom left, you can see how the movement of the electron relates to these terms, just like we saw in that silly example with the angry ox. So now that you understand the concept of what oxidation and reduction are, let's apply them to an example. Scientists often assign what are called oxidation numbers to atoms within molecules, and it's kind of just a way to keep track of who's got control of those electrons. Within each molecule, which atom has more control over those electrons. And so the more negative it is, the more control over the electrons that atom has. A positive oxidation number implies that the atom does not have control over the electrons in those covalent bonds. All right, so there are some rules to assigning oxidation numbers. I'm going to read through each of these and then we're going to use them to apply to a situation. So the first rule is that the oxidation number of an element in its uncombined state is 0. So if you just have a single neutral atom, it has an oxidation number of 0. This is also true for elements found in nature as diatomic elements. So for example, oxygen is often found as O2, so that's diatomic, two atoms combined together. And that has each atom within that molecule has an oxidation number of 0 in that case. And the idea is that each of those atoms, even though they have high electronegativity, they're playing tug-of-war against an equally matched partner. So each oxygen atom is pulling at those shared electrons equally, which means neither oxygen atom has more control over than the other. All right, rule 2, the oxidation number of a monatomic ion is the same as the charge on the ion. So for example, if you have an ion of chlorine, which has a charge of -1, you would assign that ion an oxidation number of -1. Rule number 3, the sum of all oxidation numbers in a molecule is equal to the overall charge. So if you look at methane there, CH4, you would know that the overall molecule is neutral because it's not listed as a charge. There's no superscript showing a positive or negative charge on that molecule, so it's neutral, which means all of the atoms in it, the carbon and the 4 hydrogens, those oxidation numbers need to sum to 0. We'll practice that in a little bit. Rule 4, the oxidation number of oxygen in a compound is usually -2. And again, that's in a compound if it's not just combined with itself. If it's combined with something else, oxygen usually is an oxidation number of -2. And if hydrogen is combined with something else, it usually has an oxidation number of +1. So let's see if we can apply those rules to this example. So let's go through one molecule at a time and assign initial oxidation numbers. So now we're looking at the reactants. So we have methane and oxygen. That methane is made up of CH4. Remember that they have to add together to equal 0. And we know that the oxidation state of hydrogen in a compound is +1. So if we have 4 hydrogens, each with +1, that carbon needs to balance it out. So that carbon must be -4, and the hydrogen must be +1, based on rule number 5. For determining the oxidation number of oxygen as a reactant, here we're going to refer to rule number 1. Elements found in nature as diatomic elements, the oxidation number is 0. So the starting oxidation number of oxygen is 0, because they're playing that tug-of-war, they're equally matched. So for the initial oxidation numbers, we have carbon at -4, hydrogen at +1, and oxygen at 0. Now let's take a look at the ending oxidation numbers. Here we're going to look at the products. So here we have carbon dioxide and water. Let's look at carbon dioxide first. Remember, if it's a neutral molecule, and we can see that because there's no superscript denoting a charge, that means that all of the atoms need to add up to 0. So carbon plus oxygen needs to be equal to 0. Oxygen, based on rule 4, is -2. Remember, now it's not bound with just itself. Now it's fighting with carbon over those electrons, and oxygen usually wins. So oxygen has an oxidation number in this compound of carbon dioxide of -2. Carbon then, to balance out those two -2 oxidation numbers, carbon must have a +4 oxidation number. Now if we look at water, water is combined with 2 hydrogens and 1 oxygen. We can use rules 4 and 5 to figure out the oxidation numbers here. Hydrogen is +1 and oxygen is -2. We can check that that works with rule 3, where if you have 2 positive ones, that balances out with a -2. So the ending oxidation numbers of our atoms here, carbon is +4, hydrogen is +1, and oxygen is -2. That's true in both of these molecules. If oxygen had a different oxidation number in molecule compared to the other, you would want to write out both oxidation numbers and which molecule it applies to. But because it's -2 in both, we can just write -2. All right, final question. Was which of these molecules was oxidized, which was reduced, and which kind of was neither? So let's look at it from an atomic perspective, looking at carbon, at hydrogen, and oxygen, which one was oxidized, which one was reduced, and which one was neither. So remember, when you gain control of electrons, you become more negative, and that means you are reduced. That's what happened to oxygen. Where did those electrons come from? Who lost control of the electrons? Carbon lost control of the electrons. You can see when it started at -4, that means it had control of the electrons. And it ended with a +4, and that means it lost control of those electrons. So carbon was oxidized. Hydrogen went from +1 to +1. That's no change. That means neither happened. So carbon was oxidized, hydrogen neither, and oxygen was reduced. If we look at this example of sort of imagining where those atoms, where those electrons are within each of these molecules, this might make a little bit more sense. So we think about methane. Methane is CH4. Remember that there's a really even sharing of electrons between carbon and hydrogen. That's a relatively nonpolar bond. Just for sort of ease of these problem solving, we're always going to call hydrogen +1, but really carbon and hydrogen have a fairly even relationship in terms of electronegativity. So if we were going to draw out where those electrons are hanging out, we would draw them in between carbon and hydrogen. Now oxygen, when it's oxygen and oxygen bonded together, remember that's that evenly matched tug-of-war. Each oxygen is pulling really hard, each one has a really high electronegativity, but because they're equally matched, those electrons are going to be right in the middle. Now if we look at the product side, carbon dioxide, now carbon is matched up with oxygen. That means carbon's no match for oxygen. Oxygen grabs control of those electrons because oxygen has a high electronegativity. So those electrons are shown closer to oxygen. So that's showing the polar bond of where the electrons are closer to oxygen. Similarly, in water, you see that the electrons are closer to oxygen. So here they're stealing them away from the hydrogens. So in both of these cases, carbon dioxide and water, we have polar bonds because the electrons are closer to oxygen. Now in O2, the oxygen of the reactant side, that's a non-polar bond because remember, those are evenly matched. So the electrons are not more on one side than the other. So if now we revisit those terms in terms of oxidation and reduction, if you look at the carbon of what happened, the methane, the carbon in the methane became oxidized. So that carbon, which was kind of happily sharing its electrons with hydrogen, suddenly lost control of its electrons because it's now involved with oxygen. If you look at the oxygen, the reactant, that O2, that was in a tug-of-war with itself, so no one was winning. But now the oxygen instead is in bonds with hydrogen. So you have now the oxygen fighting with the hydrogen and also the oxygen fighting with the carbon, and the oxygen is winning. Now it's able to pull those electrons away from the other atoms in that bond. One final thing I want to point out here is the idea of a balanced reaction. You'll notice that there are coefficients, those numbers in the front of some of those molecules. So it says 2O2 and 2H2O. And the idea here is that it's keeping track of how many of each atom we have. So on the left side, we actually have 4 oxygen atoms, and then on the right side, we still have 4 oxygen atoms, 2 in that carbon dioxide, and then 1 in each of 2 water molecules. We're not going to do a whole lot of balancing equations, but it is a skill that worth understanding now, and then you'll do a lot more practice in chemistry next year. So that's the end of this video. The next video is going to be on photosynthesis, and you'll start seeing redox reactions in photosynthesis. And then after that, the last video will cover cellular respiration, where once again you'll see redox in action.